call this class. Class is being recorded. Let me make you presenters. 永兴秀云 Kara. Okay, great. Oh, thank you for watching out for each other. All right, so whoever is ready, go.
Can I go?
Yeah,
okay,
go ahead.
All right. And thank you for the person that said it after me for understanding. Okay, so I'm doing 4.39 to challenge myself. So if the expected value of x equals 3 and the variance of x equals 1, first I had to find the expected value of 4x minus 1 squared. So I thought back to high school. So first I squared it by using FOIL. And then to find the expected value, I could attach or in a way distribute the e to the parts with the x value so that I could use the variance equation. I think this works. So the variance equation equals to e x squared, or the expected value of x squared minus the expected value of x squared. So I changed it around by adding this to the other side so I could get the variance of x plus the expected value of x squared, since we had that already before in the equation that I created. So I used it to get the variance of x plus the expected value of x squared times 16, which is up here, plus or minus 8, which was here, expected value of x plus 1. And then I just plugged in the numbers that I was given to get 122 by simplifying. Then to find the variance of 5 minus 2x, I remembered in class we were talking about variance, and we talked about how we could change it to a squared first in one of the examples. So I did that. So I made it just, I kind of just got rid of the 5 for a second, and I did negative 2 squared, which equals 4, which allows you to multiply right away to the variance, and 4 times 1 is just 4. So that got me the answer to that.
Great. Very nice.
Thank you.
Good start.
Thank you.
Great. Very nice. Who's next? 好。杰。
Oh, can you see my screen?
Yes.
Okay, this is a question 32 for chapter 4. To determine whether they have a certain disease, 100 people are to have their blood tested. However, rather than testing each individual separately, it has been decided first to place the people into groups of 10. The blood sample of the 10 people in each group would be put and analyzed together. If the test is negative, one test would be sufficient for the 10 people, whereas if the test is positive, each of 10 people will have also be individually tested, and in all, 11 tests would be made on this group. Assume that the probability that a person has a disease is 0.1 for all people independently of one another, and compute the expected number of tests necessary for each group. So we have two possible cases. The first case would be the group is negative. When it's negative, it only tests once. So let x be the number of test times. So this will represent when x equal to 1. Another case would be when group is tested positive. when it's positive, there will be 11 times. So we have x equal to 11. Since each group has 10 people, and for each people has negative, they have 0.9 for their probability. So we have 0.9 times 0.9 for total 10 times. So, and then this for p of x equal to 11, that's component of none of people in the group test positive. And we have 1 minus when x equal to 1. And we just plug into the formula. So we have 1 times this plus 11 times this. And once we evaluate it, we got 7.5.
Great. Great. To me, this is a very complicated question, but you analyzed well. Thank you.
Thank you.
That's it here. Okay, next one. Tom. Okay, I'll make you presenter, Tom.
Like 4.51. Suppose that
Yes.
Harry plays 10 rounds of tennis against Smith and wins with probability during each round. Given that Harry has won a total of 7 rounds, find the conditional probability that his outcome in the first 3 rounds are. For A, it's probability of win, win, and lose. The win it's 7/10, and then the second win is 6/9, and third time to get loss is 3/9. So you multiply it to get 7/40, and then the probability of lose, win, and lose is 3/10 times 7/9 and 2/8. You get 7/120 for the first 3 rounds of lose, win, and lose.
This is chapter 4.
Yeah, it's from
Okay.
chapter 4.
53. I see. Okay. All right. Thank you. That's a how.
Can you see my screen?
Yeah.
So I'm going to present question number 27 from chapter 4. So the question is, an insurance company writes a policy to the effect that an amount of money A must be paid if some event E occurs within a year. If the company estimates that E will occur within a year with probability P, what should it charge the customer in order that its expected profit will be 10% of A? So by the question, we know that the expected profit, which is 10% of A, so it's 0.1 A. And the 0.1 A is equal to the charge minus the expected value of the policy. So we need to find the expected value of the policy first, then we can find the charge. And by the question, we know that A is the money that pay for event E with the probability P. So the expected value of event E, which is P times A, equal to PA. Then by the equation above implies that C minus PA is equal to 0.18 and plus PA both sides, we will get the answer that C is equal to parentheses 0.1 plus P times A.
Okay, everything in terms of A and P. Okay, great. Very nice. Very nice. Thank you.
I'm presenting chapter 4, question 38.
Okay.
Find variance x and variance y for x and y as given in problem 4.21. So I have the picture of the screenshot from last class of question 21. So given that the variance of x is e of x squared minus e of x squared. So this is from page 145 in the textbook. So e of x squared is the equation 40 squared times 40 over 148 plus 33 squared times 33 over 148, so on, and then that we get 120,281 over 74. And then since e of x is 2,907 over 74, then that squared is 2,907 over 74 squared. So the variance of x is 120,281 over 74 minus 2,907. Sorry, this is so long. 2,907 over 74 squared. So we got 82.2. And then the similar way we find variance of y. So e of y squared is 40 squared times 1 over 4th plus 33 squared times 1 over 4th, so on, and then we get 1,453.5. And from question 21, we know that the e of y is 37, so that squared is 37 squared, and the variance of y is 1,453.5 minus 37 squared, which is 84.5.
Nice. Okay, so this is a review of last class. Thank you.
Thank you.
I want to present, Professor.
Okay.
Can you see my screen, Professor?
Not yet. Oh yeah, it's coming up. Yes, now.
I am going to present question number 4 of chapter 4, which is that 6 men and 4 women are ranked according to the time they took to complete a 5-mile trail run. Assume that no two individuals took the same time and that all 10 factorial possible rankings are equally likely. What is the probability that at least one out of the 3 highest ranking individuals is a woman? From the question we have that we have given that men is equal to 6, which denote from with M, woman is equal to 4, which we denote W. Complete mile trail run is equal to 5, which is equal to we denoted it with C, and the possible outcomes we have P is equal to 10 factorial, and the total ranking is equal to also 10 factorial. Now we have the formula is that probability number of women is ranked in first 3 position is equal to 1 minus men multiply women multiply complete trail run multiply possible outcomes minus 3 over total rankings. Let's substitute the values. 1 minus 6 we have men, and 4 we have women, uh, and 5 we have complete male trail run, 10 minus 3 10 outcomes, and minus 3 is factorial over 10 factorial. When we solve this, so we get the solution 0.8333.
Okay, I have a question.
Yes, Professor.
This is probability. Probability of no woman is ranked in first three
Professor
in first
0.863.
positions, right? So
Yes,
in
Professor.
here, yeah, 1 minus M means
Yes, Professor.
6, right?
Yes, Professor.
W is 4.
Woman.
Then complete mile run is 5.
Yes, Professor.
And P is total 10 factorial
Yes, Professor. Which is equal
minus
to
3.
10 factorial minus 3.
I don't understand this equation. Oh, okay, that's your calculation here.
Yes, Professor.
Oh, okay. All right. Okay, 1 is not in the numerator. 1
Yes,
is
Professor.
1 minus. 1 is by itself. 1 minus
1
this.
is in the numerator. Yes, Professor.
Yeah, the probability. Okay, now I see the bottom. I did not see the bottom before.
Okay, Professor.
I see. Okay, wow. It's about 83%, huh?
Yes, Professor. It's 83%.
All right. Thank you. Thank you. Nice.
Thank you, Professor.
Hi, Professor.
Yes.
Can you see my screen?
Oh, sorry. I'm trying to give them grades.
Oh,
That's
sorry.
not.
That's okay.
Yes.
Okay. Okay, so I'm presenting question 43. A and B will take the same 10 question examination. Each question will be answered correctly by A with probability zero point 0.7 independently of her results on other questions. Each question will be answered correctly by B with probability zero point 0.4 independently both of her results on the other questions and on the performance of A. Find the expected number of questions that are answered correctly by both A and B. Find the variance of the number of questions that are answered correctly by either A or B. So we have given probability of A answer one question correctly is 0.7 and probability of B answering one question correctly is 0.4. So the question A asks that we have to find expected number of questions that are correctly answered by both A and B. So from chapter 3, we have this formula. The probability of A and B equals probability of A times probability of B, which is 7 times 0.4, 0.28. Now we have to find the expected number of questions. We have the formula from the binomial random variables of n and p, which is expectation of x is n times p. So n is 10 questions, and p is 0.28. And then the answer is 2.8. And question B asks probability. We have to find the variance of the number of questions that are answered correctly by either A or B. So from chapter 3, we have this formula. Probability of A or B is probability A plus probability of B minus probability of A and B, which is 0.7 plus 0.4 minus 0.28, which is 0.82. Now we have n equals 10, which is given, and the probability is 0.82. So the variance of x is gonna be n times p times 1 minus p. Yeah, and this is the answer. These two are the formulas from chapter 4.
Oh, even the
Expectation of x
variance,
and the
the variance
variance
of
of x. Yeah.
equals n times p times minus 1 minus p. I see. I was wondering, could this be the same? It should be the same of ex squared minus e of x squared. If you calculate that, if ex squared, that would be
Yeah, I
100.
hope so.
That would be
Yeah.
28. Then ex squared. Oh no, hold on. That's for this one. Oh, you didn't have e of x for this one. Okay.
Yeah.
Anyway, so variance of x equals n times p
Oh,
times
yeah.
1.
Yeah.
All right.
Mm.
Okay. Thank you, Zakia.
Thank you.
Okay, who's next one? We have Tom, Xiuyun. Oh, Xiuyun has gone, right? Yinping, Catherine.
Hi,
Okay,
Professor.
Catherine is up. Yep.
Okay, a company LED bulbs in packages of 20 for $25 for past records and knows that a bulb will be defective for a probability of 0.01%. The company agrees to pay a full refund if a customer finds more than one defective bulb in the pack. If the company sells 100 packs, how much should it expect to refund? So according to this, we know that we have 1% that are defective and 99% that are not defective. So so the probability of getting a refund is probability that x is greater than 1. That's saying like more than one defective bulb equals to 1 minus probability of x less than or equal to 1, because we need to find the ones that are not defective plus this one defective. One minus this big parentheses right here, 20 choose 0 times 0.01 to the 0 power times 0.99 to the 20th power plus 20 choose 1 times 0.01 to the first power times 0.99 to the 19th power. We get 1 minus 0.9831 40662 equals the probability that we have like more than one defective bulb to get a refund is 0.016859. I mean, I could get reduced, but okay, so since the company sells 100 packs, so we have 100 packs times that we have more than one defective bulb, the probability 0.016859 due to 8 times 20 packages for $25, 20 times 25. We get that if the company sells 100 packs, then the refund is $842.97.
Great. Great. Very nice. Thank you. That's Catherine. We have two Catherine in class. All right. So I think we're left with Tom and Yinping, right? Okay, Yinping is up.
Hi, can you see my screen?
Yeah.
Yeah.
Yeah, it's up.
My question is 4.35. Two cards are drawn at random from an ordering deck of 52 playing cards. If the two cards display the same shade, you win $2. If they are of the same color only, you win $1. Otherwise, you lose 50 cents. And for the question A, the expected value of the amount you win. We need to find the probability of the same shade is choose one from the 4 different shades and choose 2 from the 13 cards in a shade, and over 52 cars choose 2 cars from the 52 car. So the probability of the same shade is 12 over 51. And and for the same color, it's choose 1 from the 2 different color and choose 2 from the 26 from one in one color. The probability is 25 over 51. And for the probability, either the same color and the same shade is 1 minus 2 probability is 14 over 51. So the expected value is 2 times 12 over 51 plus 1 times 25 over 51 and plus negative 0.5 times 14 over 51. The answer is 14 over 17. And for question B, the variance of the amount you win is ex squared minus ex to the square. The final answer is 475 over 578.
Okay. All right. So same suit, I understand. We have 4 suits. What
Yeah.
same color means?
We
Oh,
have
okay. We
2
have
color, black and red.
Get it. 2 black and 2 red. But they do have
Yeah.
intersection, right? Same suit and same color.
For the question is say they are only the same color only.
Oh, okay. I see. I see. All right. Okay. Thank you, Yinping. Nice. You guys presented different questions. It's very enjoyable. That's Yinping. Okay, I think this is Tom's.
Hi. Okay, so in this problem, we're given $1,000, and we're supposed to buy a commodity for $2 per ounce. Well, we have to maximize the amount of money we have, given if after a week the commodity is either $1 or $4 each. So to start off with, we have 1,000 minus 2n is the amount of money that we are starting with. So after 1 week, we have 2 possibilities where the commodity is either $1 or $2. So if it becomes $1, that's going to be half the value. So we add n. If it's 4n, if it's $4, we add 4n. So obviously, if the thing drops in value, it's a decreasing function. If it's increasing, it's an increasing function. So anyway, the expected amount of money at the end is we take the probability of each, which was given as 1/2, multiplied by the function. So 1/2 times the amount of money, depending on whether it's $1 or $4. So at the end we get 1,000 plus n over 2, where n is the number of commodity we bought, which is an increasing function, as long as n is positive. So to maximize your money earned, you just buy as much as possible. So yeah, like 1,000 times 2 is 500, so that would maximize your money. For part B, we're maximizing the amount of commodity. So we have similarly, we have 1/2 times the functions. For this one, we have 1000 minus 2n plus n and 1000 minus 2n over 4 plus n. The denominator is basically the amount of commodity we would, the commodity price, because that's the amount of commodity we can buy after 1 week, and n is the initial commodity we bought. So for part B, we get a decreasing function of 625 minus n over 4.
I don't see your B. Is your B written?
Oh, I have to press the page.
Oh, okay.
Okay, so for part B, we maximize the amount of commodity. For the n, we have the number of commodity we buy in the first week. So we have a plus n. And the second week is the part with the fraction, which is 1000 minus 2n over the price of the commodity. Which makes sense because we spend 2n in the first week, so that's just the remaining amount of money that we can get commodity with. So after we get the expected value of the commodity, we get a decreasing function of 625 minus n over 4. So it's a decreasing function, so to maximize commodity, we buy 0 in the first week.
Interesting.
Yeah,
Very
so like has very high variance. It's like the second week, the commodity could be $1 or $4. It's like in the first week you could buy 500. From the second week, the possibility is you could either have 1,000 or 125, because they gave equal probability to each outcome.
Okay, very interesting, Tom. Thank you.
Yeah.
Okay. Okay, I have updated your credits for presentation. I think that's everybody, right? Catherine, Emma, that's everyone. Anyone else like to present? Okay, let me get to my book. Okay. So last class we talked about the variance. Okay, so today we're going to talk about the Bernoulli and the binomial random variables. All right, those two are important. Bernoulli. This one. Is this good enough to see it? Oops. Make it. Okay, Bernoulli and the binomial random variables. Binomial is the binomial we know. Okay, let's read. Suppose that a trial or an experiment whose outcome can be classified as either a success or a failure is performed. If we let x equal 1 when the outcome is a success and 0 when it's a failure, then the probability mass function of random variable x is given by probability of 0, if the probability is p, right, 1 minus p, and the probability of 1 that means random variable equals to 1, is the probability of a P. So while P is from 0 to 1, including 0, 1, is a probability that the trial is a successful one. A random variable X is said to be a Bernoulli random variable. Okay, definition. After Swiss mathematician James Bernoulli, if its probability mass function is given by equation 6.1, all right? So if the probability distribution is this, success, has a certain probability, P, and so only the random variable only assigned to be two values, 0 or 1, success or failure. Okay, so that's Bernoulli random variable. Suppose now that independent trials, each of which results in a success with probability P or a failure with probability of 1 minus P, are to be performed. If X represents the number of successes that occur in the N trials, then X is said to be a binomial random variable with parameters of NP. N trials, probability for success is P. Thus, a Bernoulli random variable is just a binomial random variable with parameter 1, P. Right? So Bernoulli random variable is a special case of binomial random variable. The probability mass function of a binomial random variable have parameters N trials. Success with probability P is given by this. Probability for I goes from 0 to N. Out of N, choose I. P raised by I, 1 minus P raised by N minus I. Right, we know this. Binomial. So the validity of equation of this above equation may be verified by first noting that the probability of any particular sequence of N outcomes consisting of I successes and N minus I failure is by assumed independence of trials. Is this. So the above equation then follows, since there are out of N choose I different sequences of N outcomes leading to I successes and N minus I failures. This perhaps can most easily be seen by noting that out of N choose I different choices of I trials that result in successes. So given an example, if N equals 4, I equals 2, so out of 4 trials, the 2 successes, they equal 6 ways in 6 different ways. Namely, any of the outcomes, success, success, failure, failure, success, failure, success, failure. So this is a list of those 6 ways. Where the outcomes mean, so each of these outcomes has probability of P raised by 2P squared, 1 minus P squared, of occurring. The desired probability of 2 successes in the 4 trials is out of 4 choose 2, P raised by 2 minus P raised by 2. So by binomial theorem, the probability is sum to 1. That is, let's say this. So sum of all those trials, N trials, probability of those N trials, right? Out of N choose I successes. So all the success. Then this can be simplified to be, hold on a second. Okay, so this is infinite many trials, right? Saying probability of success, right, for infinite trials has to add up to be 1. That is, oh, okay, all right. Do you see this makes sense? Even this is the infinity, right? Infinity, so the infinite many trials, but we only pick those successful ones. So out of n, choose these I successful ones. So we'll have this binomial. This is very interesting, by the way. You know, this is from infinite world come to finite world. And to calculate this, that's p plus 1 minus p raised by n. And this equals to 1. Okay, very interesting. All right, let's see examples. 5 fair coins are flipped. If the outcomes are assumed independent, find the probability mass function of the number of heads obtained. So x equals the number of heads that appear. So we're treating getting heads as successes. Then x is a binomial random variable with parameters n equals 5 fair coins, and probability of getting heads is a half. So hence, by equation 6.2, we have no heads. So out of 5, choose nothing. Probability of success is 0. Probability of failure is 5. That's 1 out of 32. 1 head. So out of 5, 1 head. Right? Each one by binomial. So it's 5 out of 32. 2 heads. Calculation. 10 out of 32. 3 heads. 10 over 32. 4 heads. 5 out of 32. 5 all heads. 1 out of 32. So this adds up has to be 1. 1 plus 5, 6. 16. 16, 16, 32. Right. Let's see 6b. If anyone has any questions, let me know. Let's see 6b. It's known that screws produced by a certain company will be defective with a probability of 0.01, independently of one another. The company sells the screws in packages of 10 and offers a money-back guarantee that at most one of the 10 screws is defective. What proportion of package sold must the company replace? So let x represent the number of defective screws in the package. Then x is a binomial random variable with parameters of each package has 10, and the probability of defective is 0.01. So the probability that a package will have to be replaced is 1 minus 0 minus 1. Right? 1 minus the probability of no defect, because it has to be more than 1, right? At the most 1. So just do the complement, right? No defective or 1 defective, then its complement is at most 1. Right? So this is at most 1. This is at most 1. So 1 minus at most 1. It has to be replaced. So just by binomial, right? Out of 10, choose nothing. Probability of defective 0.01 raised by 0. Then 1 minus 0.01, which is 0.99 raised by 10. Then 1 defective, so 0.01 raised by 1, 0.99 raised by 9. Do the calculation is about 0.4%. So only 0.4% of packaging will have to be replaced. Good business, good manufacturer. Let's see this example. The following gambling game, known as the Wheel of Fortune, is quite popular at many carnivals and gambling casinos. So a player bets on one of the numbers 1 through 6. 3 dice are then rolled, and if the number bet by the player appears I times, so because it's a three trials, then the player wins I units. If the number bet by the player does not appear on any of the dice, then the player loses 1 unit. Is this game fair to the player? Actually, the game is played by spinning a wheel that comes to rest on a slot labeled by 3 of the numbers 1 through 6. But this variant is mathematically equivalent to the dice version. Okay, I don't know if any of you have any idea about this. Let's read this again. A player bets on one of the numbers. Oh, okay. 3 dice are rolled. That's why I equals 1, 2, 3. Then the player wins I units. Or maybe so you roll dice, you roll 3 of them. I don't know how is this played. Let's see. Spinning a wheel that comes to rest on a slot labeled by 3 of the numbers 1 through 6. Okay. So we have this spinning wheel and the number 1 to 6. But when the 3 dice, so what do you do with the 3 dice? So 3 dice are then rolled. So how do you determine winning or lose? If the number bet by the player appears I times, okay, this is how you win. If the number bet by the player, oh, okay, so they have to call a number, I guess, right? So the player says, so from 1 to 6, maybe the player said, okay, I'm betting on 5. Then you roll the 3 dice. Then what happens? The dice has 1 up to 6. So, okay, maybe one of them, right? One of them has 5. Then you win. I see. I think that's the way to win, right? Correct me if I'm wrong. Let's see now, solution. So what was the question? The question is this game fair to play? Okay, all right. So we assume that the dice are fair and act independently of one another. Then the number of times that the number bet appears is a binomial random variable with parameters 3 dice, and the number come out 1 of 6. Hence, letting X denote the player's winning in the game. So losing the game, X equals -1. So 1 winning, 2 winning, 3 winning, 3, all 3 dice. So X equals -1. What does this mean? X equals -1.
Professor?
Yes, please explain to me.
So the player has to pick a number, right, from 1 to 6.
Okay.
And then they roll a dice 3 times. And for each time you get that number, let's say you pick 4. If you get 4 all 3 times, I is 3. If you get 4 2 times, I is 2. If you get 4 once, I is 1. And if none of them show 4, then I is 0 and you lose or winning. So X is -1 when I is 0.
Oh, okay. But why do you think they use X equals -1?
Because when you get I 0, when you get I 1, 2, 3, you get I units. But if you get I 0, you lose 1 unit. So you lose 1 winning if I is 0. But if you get I 1, 2, 3, then you win 1, 2, 3 units, depending on what I is.
Okay. All right. All right. Thank you. Thank you. I think that maybe that helps everybody. Okay. I read have this losing a unit is 125 out of 216. Winning a unit is 91 over 216. All right. Thank you, guys. Okay. Thank you. Yeah, okay, so it's a binomial calculation. So this is about to understand what's going on rather than calculating. So now let's see if this is fair to play. So we want to get expected value of this. And we get -1 times, right, because this is losing one. So that's -1 times 125 over 216. Then 1 times 75, 2 times 15, 3 times 1, all out of 216. It's not fair, huh? So -17 over 216. So in the long run, the player will lose 17 units per every 216 games he plays. So it's not a fair game. Thank you. Let's see this one. Suppose a particular trait, such as eye color or left-handed, of a person is classified on the basis of one pair of genes. And suppose also D represents a dominant gene and R a recessive gene. Thus, a person with DD gene is purely dominant, with RR is purely recessive, with RD is a hybrid. The purely dominant and hybrid individuals are alike in appearance. So children receive one gene from each parent. If, with respect to a particular trait, 2 hybrid parents have a total of 4 children, what is the probability that 3 of the 4 children have the outward appearance of the dominant gene? Purely dominant and hybrid are alike in appearance. All right. So let's see this. So we assume that each child is equally likely to inherit either of 2 genes from each parent. The probability that the child of 2 hybrid parents will have DD, RR, and RD pairs of genes are respectively quarter, and a half. Quarter, and a half, right, because we could have RD and DR. Hence, since the offspring will have the outward appearance of a dominant gene if its gene pairs is either DD or RD. This is very yellow hybrid, pure yellow, pure green hybrid. Four children, right? Okay. So let's see. So this figure is saying crossing pure yellow seeds with the pure green seeds, crossing hybrid first generation seeds. It follows that the number of such children is binomial distributed with parameters. Out of 4 children, the probability of being dominated appearance is 3/4, right? Because we have this quarter plus a half, which is 3/4. Hence, the desired probability is out of 4 choose 3 children, 3 over 4 raised by 3, and a quarter raised by 1, calculating is 27 over 64. Great. Anyone has any questions for this? Interesting. Okay, keep moving. Consider jury trial in which it takes 8 of the 12 jurors to convict the defendant. That is, in order for the defendant to be convicted, at least 8 of the jurors must vote him guilty. Okay, 8. If we assume that the jurors act independently and that whether or not the defendant is guilty, each makes the right decision with probability of theta. What is the probability that the jury renders a correct decision. Okay, so this problem is incapable of solution, for there is not yet enough information. For instance, if the defendant is innocent, the probability of the jury rendering a correct decision is I goes from 5 to 12. Out of 12, choose I. Let's see. If he's guilty, the probability of a correct decision is this, right? It's 8. Yeah, it has to be 8 or more, right? 8 or more votes. If alpha represents the probability that the defendant is guilty, then by conditioning on whether or not he's guilty, we have this. We'll have this alpha times the above, then plus 1 minus alpha times this. Okay, why this start from 5? Sorry. Sorry, my phone is on my side. Okay, this is just one of the examples. This is just right. This is just one of the examples saying, you know, this is incapable of a solution. Okay, anyway, let's not care about that one, that example. A communication system consists of n components, each of which will independently function with probability of p. The total system will be able to operate effectively if at least 1/2 of its components function. 8. For what values of p is a 5-component system more likely to operate effectively than a 3-component system? In general, B, when is a 2k plus 1 component system better than 2k minus 1 component system? So it's 2k plus 1 and 2k minus 1. 8, because the number of functioning components is a binomial random variable with parameters n components, n components. Yes, it is n components. Yeah, and with probability of p, functioning probability p, it follows that the probability that a 5-component system will be effective is out of 5 choose 3, right? Because this is saying what, so A is saying 5-component system more likely to operate effectively than a 3-component system, right? So out of 5 choose 3 and out of 5 choose 4. So binomial. Then out of 5 choose 5, just 1, right? 1 minus p raised by 0, so just p raised by 5. So let's add them together. The corresponding probability for a 3-component system is out of 3 choose 2, right? Binomial. Out of 3 choose 3. And then compare those two. So which one is better? So this is saying 5-component system better if the 5-component one is greater than the 3-component one, which reduce to this greater than 0, or the square has to be greater than 0. So just 3 times 2p minus 1. That is p greater than 1/2. because this part is greater than 1, right? So that requires 3 times 2p minus 1 to be greater than 0. Greater than 0, not greater than 1, greater than 0. Divided by 3. So 2p minus 1 greater than 0, which means p greater than half. Okay, so this is a cute question. Anyone has any questions for this? Okay, this is a cute question. Then let's say the B part. B part is 2k plus 1, but 2k plus 1 or 2k minus 1. What does that to do with this probability of half? Because from the first part, we get if the probability is greater than half, 5 component is better than 3 component. Let's say B. A system with 2k plus 1 component will be better than one with 2k minus 1 component if P is greater than half. To prove this, consider system 2k plus 1 component that X denotes number of first 2k minus 1 that function. Then 2k plus 1 effective equals to probability of this X greater than or equal to k plus 1, probability of k then probability of k for k minus 1. If we do the calculation, this is for 2k minus 1. So the above is 2k plus 1. This is for 2k minus 1. That's k greater than or equal to k, which means equal to k and greater than or equal to k plus 1. Then we subtract those two. In the end, what do we get? Okay. Anyway, in the end, also is p greater than half. All right. The second part, yeah. The first part is good. Okay, let's see some properties of binomial random variable. Expected value and variance. So expected value of x raised by k. That would be I raised by k out of n choose I. So we had this before. Now we just have this I raised by k. And the I goes from 0 up to n. Yes, right? That's how we calculate. Actually, this I raised by k should be inside here out of n choose I. So this is a probability, right? When we multiply, when we do expected value, we multiply by the I term, but this is I to the k. So the I is the value of x. So if we simplify that, what do we get? Can we simplify this? Oh, okay, we reindex. So this index starts from 0. So okay, let's reindex. It's the same as I goes from 1 to n. This okay, if we reindex, this will be changed. But anyway, I don't know why they reindex this. I equals 0, I equals 1. So we use the identity I times out of n choose I equals n out of n minus 1 choose I minus 1. So this gives expected value of x raised by k equals to n times p. N times p, because we change I to be n. Change out of n choose I to be n minus 1, choose I minus 1. So we have this n times this n. Hello. This. Excuse me, I'm in my class. Oh, sorry. And then Right, so basically, okay, we use this one to substitute one of this. That's why we have a raised by k minus 1. And this is a p raised by I minus 1 because we factor out p from here. And what is the NP? NP, now this is changed to be, so I equals 1. This is to n. So starting from 1 to n. Now reindex from 0 to n minus 1. So we still have n many. Now I equals to j plus 1. So change I to be j plus 1, k minus 1. So n minus 1 now to be j. So n minus 1. I minus 1 is a j because j equals to, because I equals to j plus 1. Now change to be j. So this is just a reindex trick. N minus I becomes n minus 1 minus j. So now what happens? So by binomial, this equals to by binomial, it says this whole thing accepted as NP times expected value of, okay, so this y now, y is a binomial random variable plus 1 raised by k minus 1, right? Because this is something raised by k minus 1. So expected value of, just use another random variable y to represent, so that's y plus 1 raised by k minus 1 expected value. So what do we see about this? Expected value of x for binomial is n times p. Okay, y is a binomial random variable with parameters n minus 1 and p. All right, so x is np. So y is n minus 1p. Setting k equals 1 in the preceding equation, so that's, so this one equals to n times p. Oh, okay. So if k is 1, 1 minus 1 is 0, right? So this part becomes 1. So that's why expect if k is 1, you know, the special case, if k is 1. So expected value equals to n times p. The expected number of success that occur in n independent trials, which is, excuse me, anyone has any questions? I heard someone speaking. If we set in k equals to 2, we have e to the x squared equals to np e, then 2 minus 1, which is 1, so we have y plus 1 raised by 1. And the expected value of this, which is n minus 1p, right? N minus 1 times p, which is plus 1. Then what are we going to get? So then we have this one equals np, so we obtain variance equals ex squared. Ex squared is this minus e of x squared in the end. Okay, I remember someone used this, I forgot whom, used this one in one of your presentations, which is great. This is not strange, right? This show up in the previous in statistics class. So for binomial random variables, yeah, same as before, from a statistics class, expected value of random variable in expected value of binomial random variable equals n multiplied by p, which remember is the mean. The mean. The variance equals to n times p times 1 minus p. All right. So some of you have started, you know, ahead of me, which is great. So from now on, we can use this. all right? Because it's proved from above. From now on, we can use this. For binomial random variables, expected value is n times p, variance n times p times 1 minus p. 715. Okay, let's see this one. Proposition 6.1. If x is a binomial random variable with parameter of n trials, probability of success is p, and p is not 0, not 1. All right, be careful with these conditions. P is not 0, not 1. Then, as k goes from 0 to n, probability of x equals k first increases monotonically and then decreases monotonically. Reaching its largest value when k is the largest integer less than or equal to n plus 1p. Okay, I'm not going to go through this proof. All right, so we just use this for free. Okay, we just use this as one of our tools. But the condition is p won't be 0, won't be 1. Just a number in between 0 and 1. But it won't be 0, won't be 1. Okay, I'm not going through this example. Okay, if you're interested, you can go through this one yourself. Let's see the second proposition. Oh. All right, let's see this one. Example. So x is a binomial random variable with n6 and the probability is 0.4. Then starting with probability of random variable assigned to be 0 equals to 0.6 raised by 6. Because out of 6 choose 0, that's 1. Then 0.4 raised by 0, that's 1. That's why we have 0.6 raised by 6. And recursively employing equations 6.3. Oh, okay, this is from this. So probability of x equals k plus 1 is probability divided by 1 minus probability times n minus k over k plus 1 multiplied by probability of x equals k. Okay, this could be very useful for us in the future. Let's see the condition of k. Okay, k goes from 0 to I. Okay, so k start from 0, basically. That's what we want to know. So if we use this, right? Because we know probability of x equals 0 equals this, then we just use this above formula. So x equals 1, we have 0.4 divided by 0.6, 0.4 divided by 0.6, that is just 4 over 6. Then n minus k, 6 minus 1, n minus k, oh no, k start from 0. 6 minus 0, 6. 0 plus 1, just 1. Then probability of x equals 0, right? For this one, x equals 0, we just calculate. Then the next one equals 2. We still have this p over 1 minus p. Then now we have n minus 1. K is 1 now, right? K 1 plus 1, so on and so forth. Okay, so this is great. This is a great formula, all right? Let's see this. A computer program that utilizes the recursion to compute the binomial distribution function is easily written. To compute probability of x less than or equal to I, the program should first compute probability of x equals I, then just add to it or subtract to it. Then use the recursion to successfully compute x equals I minus 1 or I minus 2, so on and so forth. Let's see these notes. Independent trials having a common probability of success P were first studied by this Bernoulli. In his book, The Art of Conjecturing, published by his nephew, 8 years after Bernoulli showed that if the number of such trials were large, then the proportion of them that were successes would be close to P with a probability near 1. Oh my goodness. And okay, that's a family story. Okay, final example. Let's see this example. If the random variable is binomial with the parameter n equals 100, p equals 0.75, we want to find the probability of x equals 70 and the probability of x less than or equal to 70. Solution: a binomial calculator can be used to obtain the following. Binomial distribution. I don't know who has this. I don't have it. Intervalue for p, intervalue for n, intervalue for I. So probability, so that will give us interesting. Maybe I can find such calculators or such app to do this. All right, but for us, we could use, we could hand to do this, right? We could do this by hand. All right, anyone has any questions? Okay, I think this is a nice solution. And also with a proposition. Yeah, so we know for binomial, we have this expected value and variance. Proof is here. I think okay, I think I skipped the proposition somewhere. All right. Okay, that's all for today. And if you have questions, I'm here to discuss with you. If you don't, you are a free bird for tonight. Again, for those of you who hasn't presented much, prepare yourself to present. Oh, someone found it. Yeah, I found it. Let's use this. Oh, great. Let me share my screen. Let me share my screen with you. It's called a binomial distribution calculator. For us, it's 0.75. And what is our n? I forgot. Then we want to calculate a 70 number of events. 70. Let's do 100. Yes. Okay. Thank you, Ayat. Giga calculator. I'll save this website.